For multicast deployment. A couple of housekeeping things. First of all, glad you're here. Second thing, if you could try to move forward. They've asked me to ask you to try to move forward if you can. That would be, that way I can see you better. There's these lights in my eyes and all that good stuff. Second thing is, as I'm talking, please go to the microphone and interrupt me. Don't wait for me to see you. I probably won't. So do interrupt me. I'll be glad to take your questions as we go along, and we should have some time afterwards to talk about some questions as well. So my name's Bill Nicholas. I'm from the Argonne National Laboratory, just outside of Chicago. The access grid in the upper left-hand corner of my slides is the project I've been working on for the past year and a half. It's essentially a video teleconferencing system that's a architectural statement rather than a furniture statement. It is also integrated with big computers and their applications and so forth. The thing about the access grid is we've intentionally designed it for a number of reasons to require IP multicast across the wide area. So I got involved because I'm pushing multicast out there. My colleagues sometimes call me the multicast bully, because they'll take a place that needs multicast and they'll point me at them. I'll call them up and say, hey, your multicast is broken. I can help you. So, first of all, we should talk about what is multicast. Well, multicast is an IP delivery mechanism. We're all familiar with unicast. We've got a sender, a source, and a destination address on a multicast packet. In the multicast world, instead of sending to one destination, you send to a multicast group. And the intervening routers between your sender and all the receivers who are interested, they all conspire. You know, this is Steve Deering's word. I really like it. They all conspire to get the data from the sender to anybody who's interested. The sender doesn't know nor care necessarily if or who those receivers are. It's just the responsibility of the network to get it there. Again, the destination IP address is within the old Class D range, 224.0.0/4. Within that range, you don't actually have hosts listening. That's the group address. You can think of it as a place where you can get traffic from. We'll get into more of that in a little bit. A little bit of notation. You'll see this in the literature. This comes from, oh, the name's blanking me. I'll remember it later. Specific source addresses are referred to as S. The group addresses are referred to as G. If you're talking about a specific set of packets or forwarding state having to do with packets coming from a particular source to a particular group, that's referred to as S, G, and you can see how it's written. If you're talking about all the packets going to a group or forwarding state in a router or whatever, that's referred to as star, G. I may slip these into my talk later, and if I do, it's jargon, I'm sorry. And RP is the PIM sparse mode rendezvous point. That's just basically just some notations, so if I slip them in my slides, you'll know what I'm talking about. There's two kinds of multicast defined. One is, used to be called just multicast. Then it was called the Internet Standard Multicast. And then in Minneapolis at the IETF, they decided it should be called Any Source Multicast. In Any Source Multicast, the senders simply send multicast group address packets. They put them on the wire, whether it's an Ethernet or whatever, and the network takes them from there. The sender just puts the packets on the wire. A receiver takes those, learns about the group somehow, and we'll get into that later, and they register their interest in the group. They tell the network, hey, I'm interested in all the packets that might come in to the network that have this group address. That is, the packets that were given to the network by a source with a destination address of this in the multicast group range. The receivers use the IGMP version 2 protocol. I call them joins. I think in the standard they're called IGMP host membership reports or something like that. I call them joins. It's easier to remember. I know that there's some people in the back who could heckle me if they wanted to. The network, and this is important, in the Any Source Multicast paradigm, the network's job is to keep track of all the senders for the group and deliver packets from all the senders to each interested receiver for that group. I emphasize this last bullet because this is in contrast to the next slide I'm going to talk about, which is source-specific multicast. This is in contrast with any source multicast. In this paradigm, again, the senders just send multicast group address packets to the network. There's no difference on the sender side. However, in this case, receivers register their interest in specific sources that are sending to specific groups. And they do this typically by way of the Internet Group Management Protocol, IGMP version 3. And one way of notating this is that IGMP v3 does S, G joins, that is, group membership reports. The network does not need to know where all the sources are because the receiver is telling the network, hey, I want the traffic from this source that's addressed to this group. The receivers are responsible for specifying which sender's traffic they want to receive. This is the crucial difference. In any source multicast, it's the network's job to keep track of where all the sources are for a group. In source-specific multicast, it's the job of the application to keep track of where all the sources are, or any source is that the receiver is interested in listening to. Oh, one other piece of housekeeping. Can you read this? Anybody not able to read this? Okay, the buttons I've been given out are referring to reachability. If you look at one of the buttons I've been given out, it says reachability on it. What I'm going to be doing for the next few minutes is talking about this phrase reachability. And I'm emphasizing something here. In earlier time I gave a talk like this, I offered somebody $20 if they could show me in the Internet Standards where it was. Well, somebody came awfully close, so close I'm not going to offer any money. But that's for unicast. For multicast, I'm pretty sure. Reachability in the unicast world, this is what we all do every day here. What reachability means in the unicast world is it's interpreted. That is, it's not necessarily clearly defined. It's hard to go wrong from the definitions that are there, but I still don't think it's really well defined. What it means when you get a BGP reachability advertisement, what that means is pretty much send me IP packets with destination addresses that match this advertisement, and I'll get them closer to their resultant or to where they're addressed. That's kind of the social contract between autonomous systems. If I give you reachability information, you can send me packets and I'll try to get them closer to where they belong. And if you're on a Cisco router, or pretty much everybody here knows how to run a Cisco router, the way you look at reachability information for a specific destination is you type show IP route, and then you give it the address, and the router tells you what it's going to do with packets that are addressed with destination addresses. Okay? This is in contrast to the concept of reachability in the multicast. In the context of a multicast, this one I know for darn sure is not defined by Internet Standards yet. It's still in flux. Again, you can make arguments based on inferences in the standards to get a pretty good idea, but it's not well defined. What multicast reachability is interpreted by implementation in practice, that is if you go buy a Juniper or you go get GateD from Nextop or Cisco, what you'll get is this interpretation, and that is a reachability advertisement with a prefix is where to get the IP packets from sources that match that advertisement. Notice the difference. In the unicast world, you're talking about where to send the packets. In the multicast world, you're talking about where to receive those packets from. Whether you ask for them or whether you just receive them, that's a little bit more detailed. The point is, it's inverted from what you might normally expect. Now, in a Cisco router, again, because it's most common, the way you can find out where you're going to get packets from a given source is through this command, the show IP RPF. This is equivalent to the earlier command I talked about for unicast, show IP route. There's another command we use in Cisco to talk about multicast, but this is the command you use to see reachability. The other command you may have heard about is something else entirely, and we'll get into what that is in a few minutes. So here's an example. Now seriously, I hope you can read this. What I did is I took the machine that I run my screen session on back at the lab, and I ran netstat -rm. This is a pretty typical Linux box. You can see on the first line, you've got headers and so forth. The first line talks about the reachability for the interface. In this case, the interface has an IP address of 140.221.11.103. There's no gateway. That doesn't make any sense in the context of an interface. Its net mask is a /32 because, again, this is an interface. It has a single host route, or is a single route. And you can see which interface is associated with. It's ETH0, Ethernet 0. You know, if it was multi-homed host, it would have different options, but anyway. Now, the second piece of reachability information this particular host has is the subnet to which it's directly connected. As it happens, this machine is connected to a network that has a net mask of /22 because of the number of hosts on it. As you can see, the base address for this prefix is 140.221.8. Again, there's no gateway involved. This is the local network. Its net mask, as I said, is a /22. The flag is U for it's the network. And again, if it wants to get packets to 140.228.0/22 destinations, it's going to go to ETH0. The next line is pretty standard on pretty much any Unix box or any IP host really. If you want to get to the 127 network, you go to the loopback device. It's always internal. Nothing strange here. And skipping one line, we look at the last one, 0.0.0 with the net mask of 0.0.0. That's the default route. Here the gateway makes sense because that's the default route to the outside world, 140.221.11.253. You know, that's an HSRP address for a couple of routers. You all know the drill. Again, but this time we have a gateway address, a gateway flag, and an interface. It says if you're going to go to that gateway, you use that interface. This sounds pedantic, but I'm setting the stage to explain the next to the bottom line here. The next to the bottom line is the multicast line, okay, where we have the reachability information for multicast. The reason we know it's multicast is because where it says destination, it's 224.0.0.0, and the net mask is the /4. What this is telling the kernel is if you're interested in multicast traffic, where you go to get that traffic is that Ethernet interface. This has nothing to do with where the traffic is sent. It has, well, it may have something to do with it. But the point is, it's more important to remember that this is where the multicast traffic is going to come from. In fact, this is one thing that was not in the standard Linux distributions that we had. We have to put this static route in there to tell the kernel, if you're going to get multicast traffic for your clients that are running on your, on your platform, you have to get that traffic from the Ethernet interface. That's where you talk IGMP version 2, in this case, out of. This is reachability on the host side. Again, we have the duality here. We have the where does the traffic come from and where does the traffic go to, depending on whether you're talking multicast or unicast. Here's an example of reachability for on the Cisco box. Okay, this is my border router. Kiwi is its name. Here, the border router is a couple hops away from the host I was talking about, but I'm going to talk about reachability in terms of unicast right now. So I do the show IP route, and I put the IP address in for the host, and we get the sort of standard stuff we're used to seeing. It happens that I'm running OSPF. You can see the distance, the metric, all that good stuff. It's got a gigabit Ethernet interface. It heard it 3 hours ago or whatever. And when it wants to send a packet somewhere, it's going to send it by way of gigabit Ethernet 5/0, and it's going to send it to the next hop, which is 140.221.20.124. That happens to be the IP address of the intervening router. Again, no rocket science here. This is what we're used to doing on a day-by-day basis. On the other hand, if my router says, I need to get traffic from 140.221.11.103, this is how I find out where this router is going to get that traffic from. It's a different command, show IP RPF. In this case, it tells me that it's going to get the traffic from interface gigabit Ethernet 5/0, no surprise, same sort of thing. The RPF neighbor is this router that we referred to earlier. The route and mask, it tells me where I got that information from. In some cases, you may have divergent unicast and multicast paths. In this case, we don't. And some other information. Emphasize here, the unicast and the multicast paths may diverge, and you use different commands to look them up. Unicast, you use show IP route. Multicast, you use show IP RPF to find out what that topology is. Okay, some of us may have heard of the old M-bone. Some of us may still be on the old M-bone. The slide here used to be why the M-bone should go away, and somebody yelled at me and they were right. The old M-bone is an excellent first approximation. This hadn't been done before, and so it's really hard to fault the people who started it. The M-bone architecture used tunnels to get multicast traffic across the unicast-only network, the old internet. The routing was done, again, this was an experiment, it was done by user space daemons run on general purpose Unix boxes, typically Sun 3s. The IGMP protocol, Internet Group Management Protocol, was developed in this context. This is one piece of the old M-bone architecture that hasn't changed until we get to SSM. IGMP turns out to be a very good interface, and we've held that over. Another thing about the old M-bone, people sometimes get confused between the M-bone and an application used on the M-bone called SDR. Notice that the M-bone predates the World Wide Web. The reason that the M-bone has this session directory application so tightly associated with it is because you had to have a directory system to find sources or sessions that you were interested in. And you didn't have the infrastructure we have today for the World Wide Web. So that's why you'll see SDR sessions referred to a lot of the time. In fact, at this particular conference, there's two ways to get the information about the multicast group. You can get it off the SDR, or you can get it off the NANOG web pages. Either way will work. Some lessons we learned from the M-bone. Yes, sir?
The use of SDR there. One nice aspect of using multicast to distribute the program information is that then scoping rules allow it to go to exactly the same places as the program information can go. And so there can be problems when using the web as the mechanism for making program listings, that you can find a listing for something that you can't actually get access to.
I'll go into this a little further. I will, in theory, I agree with you completely. There's some practical problems with that, however. I'll get into that a little later. Some lessons we learned from the M-bone. For the first thing, the first lesson that's come out of this is that the M-bone routing protocol, DVMRP, simply doesn't scale, okay? It's essentially the multicast equivalent of RIP. I doubt that there are many internet service providers today who will give their clients a full feed of unicast routes using RIP. If there are, I'm sorry for your customers, I don't know. But that's what DVMRP did, is it flooded the reachability information for sources on a regular basis, just like RIP does. Because of this, and because of some other things about it, it was easy to create IP multicast amplifiers. This is where you get reachability. It's like a routing loop, but instead of just being a routing loop, at every hop you're spewing off additional packets from every hop because it's a tree fan-out thing. And so you'd end up melting the place down if you had a routing loop, not just the links involved. Another problem with DVMRP in the M-bone implementation is that it involves separate routing infrastructure that wasn't aligned with what became BGP. So this was an application test bed as opposed to something that could be managed as a service with all of the policies that are involved. Another thing that they learned from the M-bone is that a technique for multicast routing called flood and prune doesn't scale. Flood and prune is where let's say I'm sending traffic. I send you all the traffic that I've got until you tell me to stop. I refer to this as hurt me until I tell you to stop. Okay? The reason this doesn't scale, there's several reasons, but two of the big ones here. It's not sensitive to the available bandwidth. Okay, I will keep sending you traffic regardless of whether you have receivers that care, whether or not it oversubscribes your links. It doesn't matter. I just send you the traffic until you tell me to stop on a regular basis. And the second reason is that in this situation, the failure modes are horrible. If your router can't handle this kind of traffic, if it can't keep up with this kind of traffic, if it can't send you the prunes because it's overwhelmed or crashed or something, you're just going to keep getting the traffic, and you're going to be stuck in this stable state of being down. This is not a good thing. So it requires downstream routers that are powerful and smart enough to be able to send all the prune messages necessary. This is a feature of a flood and prune protocol. Examples of a flood and prune protocol are PIM dense mode, and again, the original implementation of multicast routing, DVMRP. DVMRP did both the reachability and the forwarding, and it had these problems with it. So some of the lessons that have been applied to this. The multicast border gateway protocol, and I got the wrong slides. Oh, no I didn't. This is not the multicast border gateway protocol, this is the multi-protocol border gateway protocol. I forgot to update this. The multi-protocol border gateway protocol, it provides reachability and policy control for multicast routing, just as it does for unicast routing. You have all the knobs ranging from length comparisons to AS path length comparisons to local pref to metrics. All of those things are available to you with the multi-protocol border gateway protocol. Second thing you need is a forwarding scheme. That is actually how you move packets from one autonomous system or one router to another. And the protocol that has ended up sort of winning the Darwinian evolution battle here is the protocol independent multicast sparse mode, or PIM sparse mode. Where protocol independent multicast, the protocol independent refers to the fact that it's independent of the underlying reachability protocols. So you can run PIM over a network that uses any other reachability protocol underneath. This is again in contrast to DVMRP, where DVMRP had a combined reachability and forwarding protocol. Features of PIM sparse mode include listeners receive traffic only when they want it. They have to do something affirmative to get traffic, and they have to continue to do something affirmative to get traffic. Second thing that the PIM does, again, sort of like DVMRP, it forms a multicast distribution tree. That is, you start with the sender, and you go from the sender to the local designated router, and as necessary, you get a branching structure, tree, that distributes traffic from the sender to all the receivers. A feature of this tree is that no more than one copy of the packet needs to traverse any edge on that tree, which makes for very efficient distribution and packet replication in terms of link bandwidth requirements. MBGP is good, PIM sparse mode is good. The thing with PIM sparse mode is it only scales so far, typically within an autonomous system. So what you need is another protocol to distribute the knowledge of all the available sources in the internet, and so a protocol called MSDP, or the Multicast Source Discovery Protocol, was developed. Multicast Source Discovery Protocol is a way for PIM sparse mode rendezvous points to talk to each other, to tell each other where the active sources are, so they can form these trees between PIM domains. A PIM domain is a set of routers that share a PIM rendezvous point. We'll get into this in a little more detail later. So drilling down a little bit further into each of these protocols, multi-protocol BGP comes from RFC 2858, where it adds the MP reach NLRI attribute to BGP. What this does is it identifies a reachability advertisement as whether it's unicast, whether it's multicast, or for efficiency, whether it's both. There's 2 bits and 00 is undefined. So that gets you your 3. As I said earlier, when implementing a router, you get all the standard BGP machinery for choosing reachability that you're going to use and forwarding it to your peers and all that good stuff. It's just exactly the right thing you need for scalability of reachability information in an internetwork of autonomous systems. Another thing to be aware of is that multi-protocol BGP routes can be independent of, that is, the topology of reachability can be different between unicast and multicast. So you may decide that some set of your peer autonomous systems you'll only exchange multicast with, or that you'll only exchange unicast with. This is actually pretty common. Some of the research networks have considerably more open peering policies for multicast traffic than they do for unicast traffic. I'm not going to try to figure out why, but that's just the way it is. And this supports that model, where you have differences between your multicast and your unicast peerings. It allows that topology to be generated and used in two separate ways. So to configure multi-protocol BGP, I'll go through these slides reasonably quickly, but I've got configuration information here for Cisco, for the next top technologies GateD, as well as for Juniper. So you can get a flavor for what do you have to do to bring up reachability, multi-protocol BGP reachability communication. So differences here, on the second line, you add the NLRI unicast multicast, which tells the router, hey, this prefix that I'm putting into BGP will be used for both unicast and multicast. You tell it on your neighbor statement that you're going to be exchanging unicast and multicast routes. The rest of this is standard stuff, description, VBNS, soft configuration. And then you have a route map, and for inbound and outbound. When you go to see what the route map looks like, what I'm showing here is that you can treat the inbound and outbound prefixes differently. You can set them to different values if you wish. You can filter out prefixes from unicast and not from multicast or vice versa. You can set different MEDs or local weights or local prefs, whatever you want to do. Let's see, access list 50 is the list of prefixes. I used that in the earlier config or the earlier, and here's a prefix list again that I used in the route map. These slides are in the talks also, we'll skip by them. For GateD, it's a similar sort of situation. You're basically telling it you're going to be speaking MBGP, and there it is. One thing in MBGP in GateD is it specifically calls out the fact that there are two routing information bases here. You've got a unicast routing information base, a RIB, and a multicast one, and it talks about how you're going to be importing and outputting for that. And again, this is talking about where you're going to be sending these networks to Autonomous System 145 again. In Juniper, Juniper has several routing information bases. INET.0 is your unicast forwarding table. INET.2 is your multicast reachability table. I think INET.1, I don't want to guess. I know that INET.2 is your multicast reachability table. You can look in the Juniper documentation. There's people from Juniper here who can tell you all about it. What they're doing here is they're putting in some static reachability information into the INET.2 routing information base. Just basically, these are the multicast equivalent of static routes. Again, multicast world, you're telling it, if I want traffic from these places, this is where I'm going to get it from. In the case of multi-protocol BGP, you're talking about, you have to tell the various protocols which sets of reachability MIDs you're going to be using. This is some examples. Again, you see INET0 and INET2. You see for the multicast routing group, it's INET.2. For the interfaces that are capable, those are INET.0 and INET.2. You can get into more detail about this. What you need to take home from this is that there are two tables of reachability information. Here's where you set up a peer if you have a Juniper. In protocol BGP, this is a peering between one of my peers in Argonne where I work. We've got the policy, who you're going to accept, what prefixes you're going to accept from them, what prefixes you're going to announce to them, what their peer autonomous system is, what their IP address is. Again, this is very similar to a unicast peering. You just have a couple extra statements to make sure that multicast reachability information is being turned on. When you want to look at this, Cisco also has two sets of reachability information that you can look at. In Cisco, if you want to look at the multicast reachability from BGP, you use show IP MBGP commands as opposed to show IP BGP. Show IP BGP is unicast, show IP MBGP is multicast. So here's an example of running show IP MBGP sum. I've taken out all but one of them. You can see the typical stuff, the neighbor, the version, the autonomous system, yada, 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 and the number of prefixes you've received. These prefixes, again, are multicast reachable prefixes. If you do it without the M and BGP, in the case of, at the time, there was a lot more. I'm not sure what the differential is anymore. I haven't looked. If you want to look at a specific prefix, again, this is sort of standard stuff. You do show IP MBGP to look at a specific address to see what reachability information you have for it. As you can see here, we've picked number 2. where it's coming from VBNS to, I think that's SOX, but I could be wrong, 10490. And we've picked that reachability information over the longer autonomous system path information from AS24, the NASA network there. You know, for obvious reasons, it's a shorter AS path. On a Juniper, you want to do the same sorts of things. You do a show BGP neighbor, and you give it the IP address of the neighbor. You get a bunch of information, but the key thing you want to look for in this is the NLRI is advertised for iNet unicast and iNet multicast. For the session, it's iNet unicast and multicast, and that you are, for table iNet.0, which is your unicast, and iNet.2, you are receiving prefixes from your neighbor that go into both ribs. That's, you know, what you do to look at up here. Here's another example, just like the Cisco one. This isn't my router, so I was able to use my host address. You can see that they have quite a few paths, multicast reachable paths to get to me. The one they're choosing is the direct path, AS path 683. They could go by way of Abilene, 11537, just to me. They could go by way of VBNS to me. They could go by way of their campus network to me, or they could go by way of Vario to me. You know, that's the reachability information they have. And again, in situations like this where you're multi-home, you need BGP to make the decision for you in terms of reachability. I don't have a gate key monitoring slide, I'm sorry. Move on to PIM sparse mode. Multi-protocol BGP gives you the reachability information. This is a relatively static topology, if you will. Now when you want to talk about actually moving packets around, the protocol you use for this is, well, that is typically used for this is PIM sparse mode. Somebody a couple of weeks ago asked me if PIM is a Cisco thing. The answer is very much no. It's an RFC, it's a standard, it's implemented by a bunch of people. You can get it from a lot of different vendors. RFC 2362 defines sparse mode. One of the nice things about PIM sparse mode is there's no activity in PIM sparse mode until either a host starts transmitting traffic, at which point you have to do some PIM stuff, or if a host subscribes to a group. If neither of those things happens in your network, you don't get any PIM sparse mode activity. That means a few things, one of which is that you can't debug it if you don't have sources and receivers. In PIM sparse mode, you define a rendezvous point. In order to distribute the knowledge of the active sources, you have to have a rendezvous point that gets the information from about all the sources and redistributes it down a shared tree for each group. So that's what PIM sparse mode does, is it creates a shared tree rooted at the rendezvous point, which is defined typically by configuration. There's some automatic ways to define where the rendezvous point is. I prefer configuration for reasons we'll get into. Given enough traffic being sent to the rendezvous point, well, what happens is that the traffic gets from the source to the designated router on the local network. It's encapsulated to the rendezvous point, then down the shared tree. If you get enough traffic, the rendezvous point says, hey, everybody, look, don't get the traffic from me, get it from him. He's the one sending it. And so everybody then does source-specific joins towards that source. This is called a source-based distribution tree, and typically enough traffic to trigger the creation of these is typically anything greater than 0. It just works better that way. Another thing to be aware of is that anytime you've got traffic moving between PIM domains, those distribution trees are always but always source-based. Those are source-based. There is no such thing as a shared tree in current practice between autonomous systems or between PIM rendezvous points. I see somebody coming to the microphone. No, okay. Here's a diagram that I would use. I've already walked you through most of it. If you're using a shared tree, what that means is the sources packets is grabbed by the router A in this case. Sources at the top, receivers at the bottom. Router A grabs that packet, encapsulates it in a unicast packet, sends it to the rendezvous point. The rendezvous point then sends it out to anybody who's interested in that group. In that case, it's router C. Okay? If there's enough traffic, that announcement, or that traffic that gets sent out the shared tree has a bit set that says, you know, you really ought to create your own source-based tree. So router C will send a message, hey, I know you've got this source there. I want traffic from it, and router A will send the traffic directly from router A to router C and then to the receiver, which obviously is more efficient rather than running into the rendezvous point that could become a bottleneck. Okay, that's great within an autonomous system. If you've got a bunch of autonomous systems, you want the rendezvous points in those autonomous systems to be able to communicate the knowledge of active sources. In order to do that, we use a protocol called MSDP. This one isn't yet an RFC. It's real close. Last I saw, we were either entering or in the last call stage. It may have gone actually out of the last call stage. I haven't been following closely. It's being done out of the MSDP working group of the IETF, and there's the draft if you want to go read it. Currently, it only covers IPv4. There's some talk that IPv6 should be done a different way. That's still under discussion. Again, the rendezvous points communicate amongst themselves to find the active sources. And then once they have the active sources and they have interest within their domain for those sources, they send PIM sparse mode joins toward each other. Those are source-specific sparse mode joins towards each active source. And then that's how they graft onto the internet-wide distribution tree for that source and that group in the internet. I should also say a couple things about MSDP that aren't on my slides. One of them is that the MSDP connections between autonomous systems or between PIM rendezvous points are TCP. They're not UDP like other things. And MSDP also follows the reachability information typically from multi-protocol BGP like PIM sparse mode does. So it's a flooding protocol, but the flooding is extremely constrained. It should not flood the knowledge of a given source more than once a minute. And currently, scalability doesn't seem to be a problem. I think last time I looked, we'd gotten up to like 3,900 sources in the internet. CADA does a good job of tracking that over time. Okay, reachability again. I've got a whole bunch of these pins. And now you can understand what I mean by these pins. Reachability. There's two things to dealing with reachability. You have the where-to of reachability for unicast, and you have the whence of reachability for multicast. It's a duality. These pins say both of them. I've got pins on both ends of these tables if you want to come pick them up whenever. A BGP NLRI multicast route is a statement of reachability. In this case, reachability means the ability to get traffic from a given source. Interdomain PIM sparse mode joins follow that reachability. The traffic coming back is the inverse of that topology. Reachability is a directed graph, you could think of it that way, and the traffic follows the reverse of each edge of that directed graph. Again, MSDP forwarding between rendezvous points follows a BGP reachability topology. That's rule number one in the MSDP draft pretty much is, if you've got the next hop and it's that direction, that's where you accept things from. This means something, and that is if you're announcing something with MBGP, this goes back to my earlier thing where MBGP or protocol BGP multicast semantics, reachability semantics are defined. In practice, if you're doing multi-protocol BGP, even if you're doing PIM sparse mode, if you're not doing MSDP, what you've just formed is an MSDP black hole. We ran into this earlier this year in the December, January, February timeframe where there were some MSDP storms and some transit networks just turned off MSDP. This was not good because the sources behind them, their customer sources, the knowledge of those sources were not made available to the rest of the internet. And we couldn't get their traffic because our routers had no idea that those sources even existed. So turning off MSDP, if you've got multi-protocol BGP turned on, is a bad thing. And here I am standing in front of NANOG saying, please don't do this, it hurts. That's one of the reasons I'm here. They pay me to come up and say these things. Okay, configuration for gate D and for PIM sparse and MSDP. I'll run through these real quick. I didn't get any MSDP configuration for gate D. I understand it's coming soon. PIM sparse is really easy to configure on gate D. You say, I'm going to do IGMP on this interface, and I'm going to do PIM sparse. That's pretty straightforward. In Cisco configuration, you do a combination of interface commands for PIM sparse mode configuration, and you do some global mode commands for MSDP. On the interface side, the two things you add on a peering between you and somebody else is four things. First of all, you say PIM sparse mode between you and another autonomous system. You say you're a PIM border. That way, you say you're a PIM border and you put a boundary with an access control list. There are some automatic discovery mechanisms implemented, AutoRP and RP discovery, that allow a network to automatically self-discover where the rendezvous point is in PIM. For reasons having to do with debugging, I don't like that. That's sort of an engineering decision, but that's sort of where I come down on the engineering decisions. One thing that's important, though, to do is to make sure that you don't advertise your rendezvous point to somebody else, or you don't accept advertisement for somebody else's rendezvous point. That would not be a good thing. Things get very confusing in that situation. So you put in a border statement, which does one of them, and then there's a IP multicast boundary with an access control list number you use to do the other one. I don't remember whether it's, anyway. Another thing you say between autonomous systems is you put in a threshold so that packets that don't have a TTL this much or more, they don't transit this peering. This is useful so you can do scoping of where this multicast traffic is going to go based on TTL. Let's see. So the access list 10 here is just the Cisco RP announce. You don't want this traffic either leaving or entering your network, and you also probably don't want traffic in the administratively scoped range to enter or leave your network. And so that's the access list that is associated with that interface statement. MSDP peering is, again, it's just a peering configuration. You've got an IP address, description. You decide what to filter incoming and outgoing. We'll look at that ACL in a minute. SA request and TTL threshold. SA request says, when I bring up the peering, send me all these source advertisements you've got. Otherwise, you'd have to wait for up to a minute and a half for all of them to populate your cache. This just bootstraps it quicker. And the last line is now obsolete because as of the latest draft for MSTP, SA caching is mandatory. Access list 111, this is partially what's out there. I'm working on a draft that will try to codify this in the more. You want to stop some things, like, for example, you don't want, let's see, Sun RPC. You probably don't care to do an RHU minus A and get everybody in the internet. Maybe you do. I don't want you to be able to, okay? Another one down there is the old SGI dogfight. I really enjoy that game. Unfortunately, the tradition of filtering this happened when that was just too much traffic for the internet. Nowadays, the people who put SGI dog there would probably be filtering all the. Do you know that there's now an implementation of Quake that uses multicast so you can watch players in a tournament? That would probably get put on there because it's at the same level. Some other things you want to deny. You want to deny the administratively scoped areas, assuming you want to control the administratively scoped areas within your autonomous system. That's an assumption. You want to filter the Martians, and then after that, you want to accept any. You might, if you're not a transit network, also only permit outgoing addresses that you own as sort of a belt and suspenders approach. Okay, I don't have all the details on Juniper. MSDP lets you do the same things, but we'll go through the PIM and MSDP now. For PIM, you have to tell PIM which routing information base group you're going to use. You tell PIM in Juniper, and I don't have the Cisco stuff, but you should do the same thing in Cisco. You say the rendezvous point is going to be local and its address is going to be, in this case, on the border router. And you say all the interfaces should run PIM version 2 sparse mode. Again, pretty straightforward. For MSDP, again, use the multicast routing group, RIB group in this case, and this shows a peering between this router and my network. You have a peer and you have a local address. The local address in this case is the rendezvous point address. From this, you can probably figure out where this router is. Oh, MSDP also in Juniper lets you apply import and export policies here, which is highly recommended. It's just I don't have that example here yet. Okay, again, how do we monitor each of them? How do we look at them and see which ones are, how am I doing? How do we look and see how things are going? First thing you want to do with MS is make sure that MSDP has actually come up. On Cisco, you can do this with the show IP MSDP sum, and you can see the peer addresses there. In this case, this was my peering with VBNS AS145. Peer address stayed up. This is good. It's been up for a day and 12 hours. It's been reset 11 times since I set up the peering, and you'll do the DNS lookup on the name. In Juniper, it's a very similar command. It's if you want to look and see if the peering is up, it's a show MSDP peer. Give it the address, and you get back, again, the peer address, the local address you're using. It's established, and it's been up for 2 weeks, 5 days, 18 hours, something like that. It's up. This is a good thing. You can get into more detail on both of these. Next thing you want to do, if in fact you've got MSDP up, you want to make sure that you're getting active sources. That is, you've got reachability information that's being properly interpreted. On Cisco, you do a show IP MSDP SA cache. In this case, I'm looking up a particular multicast group. I get lots of entries there. The entries here, we need to go talk about just a little bit. We see these two addresses in parentheses. That's the S, G I was talking about, the source and the group. MSDP tells you the source and the group of an active source. It also tells you the rendezvous point that generated this source announcement. So that's the third address. One thing that's commonly not understood with MSDP is that the reachability information that MSDP uses is not the source. It's the rendezvous point that generated the advertisement. This is important if you're setting up MSDP, so you make sure that your rendezvous point address is actually advertised by you for multicast purposes. Otherwise, your MSDP peers are going to drop all your stuff on the floor, and that's not a good thing. Again, the MAGP AS145, that's just a lookup in the reachability table. And from this, it looks like that source has been active for 3 hours and 40 minutes. And that source will expire in 5 minutes and 3 seconds unless we hear another announcement of it. And in this case, if you do this right now, you'll get a bunch of these. In Juniper, you can do the same, or the equivalent command is show MSDP source active, and then for group, and this is a different group. Again, you get the group address, you get the source address, you get the peer from which this was heard, and the originator is the rendezvous point that originated this in the first place. So as you can see, this router is getting this announcement from 4 of its peers, but they're all coming from the same rendezvous point. Now, if you're going to be, assuming your router knows about the source and you've got interested listeners, you want to do a show IP mroute count. That's actually not right. That's wrong. I think that's show IP mroute. Anyway, it's a command very much like this. I may have count in the wrong place. It should be at the end probably. What this tells you is that in this group, go down to the very bottom, in this group 224.2.177.155, source 128.163.3.214, it has forwarded 7,089 packets. It's getting 0 packets per second. This is not a good thing. The packets that it used to get were about 480 bytes and kilobits a second is 0. This is how you tell to see if packets are actually coming into your network properly from the outside. Now, assuming they were, one thing you want to know is from which peer am I actually asking for traffic, and which of my interfaces am I sending traffic towards? This is where you use the show IP mroute command. Notice that this has nothing to do with reachability. This has to do with actual packet forwarding state. Don't confuse show IP route with show IP mroute. They're orthogonal in function. In this case, looking again at this source, The source is 128.163.3.214. In the group 224.2.177.155. This state has been there for 3 hours, 55 minutes. It's going to go away in 3 minutes if there's no traffic. Flag M, meaning it was created by MSTP. T is it's a source-based tree, which is sort of the way they've all got to be because it's an MSTP thing. The incoming interface. This tells me that the traffic should be coming in on ATM 3/0.145. I happen to know this is my peering with Abilene, Autonomous System 145. The RPF neighbor is 192.5.170.130. That's the address of my peering with BBNS. And it shows me that this router has received requests for traffic from that source on 2 of its interfaces, ATM 0216 and ATM 0200. So this router is receiving, if it were to receive a packet, it would come in on the ATM 3/0145 subinterface. It would replicate that packet and send 1 copy out each of ATM 0216 and ATM 0200. Juniper has a very similar command, of course. Show multicast route group 233.2.171.1. Source prefix, again, a source address, and then I use the word extensive to make sure I get all the same information. Here you've got the group address, you've got the source prefix, it's a /32 because it's a source specific thing. You can see the number of packets that have come in on this. It is, the upstream interface is ATM 100.683, that's their sub-interface to get the packets from my source. And I guess I missed it, but you can also find out, I don't have the command here, unfortunately, what the downstream interfaces are with Juniper. I'm sure the Juniper people know, I just forgot to put it on the slide. Important thing to remember here again is this is not reachability information. This is actual packet forwarding information based on active sources and active receivers. Oh, this is the downstream. So if you want to see who has sent you joins for sources, use the show pim join command, and it tells you the upstream interface is and the downstream interfaces are. Going back to this one, the useful thing is I've run the same command twice. You can see the packets are coming because the packet count is higher in the upper one than the lower one. So you just use the up arrow return to make sure the packet numbers are incrementing. Here you can see where they're going to and where they came from. Show, pin, join, etc. Okay, some tips. Somebody said that an expert is somebody who's made all the mistakes in a very narrow field. Here's some tips from somebody who's made a lot of mistakes. On an ATM peerings, this is best done with point-to-point subinterfaces as opposed to point-to-multipoint. One way to sort of think about this is in a point-to-multipoint subinterface, what you're doing is you're emulating a multi-access network. In a multi-access network, the PIM sparse mode protocol requires you to elect a designated router. What this really is a bunch of point-to-point interfaces. A designated router needs to be able to see all the traffic in the multi-access network. So I'm not even sure what a designated router in the context of an ATM exchange point is. There are some extensions to PIM sparse mode that allow you to use, I think it's called NBNA mode or something like that. My experience, this is my experience talking here, is that it's better to do this with point-to-point subinterfaces, and my experience is you don't have to interact with your peers in order to make all of your unicast connections point-to-point. It's a little longer in the configuration, but when you go to turn on multicast, it's very much simpler to debug and operate. Another thing to be aware of, MSTP source active messages are essentially just PIM register messages. Somebody may complain to you that your autonomous system isn't sending them MSTP source active messages. This problem may not be on your border router. Chances are this problem is at your designated router right next to your source. There are some, unfortunately, there are some bugs in designated router implementations where they stop sending PIM registers, which means that border router stops sending Source actives, which means the rest of the world doesn't know to start sending joins towards you. The way you know this is happening is because some people who've been listening to your source for a while continue to get the traffic, but somebody else who gets interested in your source can't get your traffic because there's no knowledge of that source out in the internet. If you want, I can tell you the bug numbers and all that good stuff, but this is something to keep in mind. MSDP encapsulates data in its source active messages, just like they were encapsulated in the PIM sparse mode. This is going back to the earlier question. From what I can tell, this was done primarily to support bursty sources, they call them, or sources that don't transmit enough to have a source-specific tree, or are not judged worthy to have a source-specific tree. And I believe because of the low frequency of advertisements of SDR, this was one of the driver applications. Another one people have talked about is NTP. What worries me about NTP is that NTP really truly does want to know what the round trip is like, and I'm not sure what round trip means in the context of multicast. So what this ends up saying, what I've observed, the scar I have, is that it's possible for MSDP to be operating correctly, but PIM sparse mode is not. Again, this goes back to one of the big reasons often is because they're using point-to-multipoint interfaces. It looks like PIM is working. You've got the reachability information from multi-protocol BGP, but you can't actually do any joins. The problem is, if the debugging tool you're using is SDR, you're getting a bad view because this data is encapsulated in your MSDP source actives. It gets sent down the shared tree within your PIM sparse mode domain. It shows up on your display as you've got sources. But if you try to click on them, you don't get any source, you don't get any actual traffic because things are broken. And it's really hard to tell unless you have active sources and active destinations. And SDR doesn't count because of its low frequency and the fact that its data is encapsulated in MSDP. So these are some of the tips. We'll lead into a little bit about debugging here. And, okay, we're not doing that. Let's talk about debugging multicast. As I've said 2 or 3 times already, in order to debug multicast, you must have at least one constantly active source. When the internet was small enough, you could coordinate the people who are going to do the debugging. Today, you file trouble tickets, and you coordinate trouble tickets between NOCs. You can't assume that you're going to get end-to-end people on the NOCs for a non-emergency situation like multicast debugging. So what you must have is at least one constantly active source, and you've got to have at least one constantly active receiver. Otherwise, the MSDP state doesn't matter or doesn't get created, the PIM sparse mode state doesn't get created, and you cannot debug this without an active source and an active receiver. Once you've got that requirement, that pair of requirements met, you can start near the receiver. The first thing you need to do, assuming you're using PIM sparse mode and all those good things, is look at your router attached to that network that the receiver has. You need to identify the PIM sparse mode designated router. Now you may say, duh, it's this router. I know it's this router because it's the one I control. Well, I spent 3 days because I made that assumption. You really need to go into the router and say, hey, are you the designated router? Maybe that Ethernet switch over there that doesn't have layer 3 forwarding turned on is a PIM sparse mode designated router and it got elected. Okay? You really need to go look at the designated router to make sure it really is the designated router. Then you verify the IGMP state in the designated router to make sure that it has gotten the host membership reports, that is the IGMP joins, and that it has it's got the appropriate state in the designated router. If it's got only group state, then you know that it's not getting source information down the shared tree and so forth. But that's where you start. From the designated router, you follow the reverse path forwarding from the designated router back towards the source. On each hop, you verify that PIM sparse mode has been configured for each interface along the RPF. PIM sparse mode has no clue if pin sparse mode hasn't been configured upstream. It follows the underlying reachability information, so you need to verify steps along the way. You also might think, just for a few minutes, I'll just set up multicast on this subset of my network. Well, if you do that, it's dangerous because with outages or who knows why, your reachability may change with a dynamic routing protocol, and that reachability information may be going away you didn't expect. Follow the RPF based on the reachability at each router. At each point, check the S-G state. Make sure that the appropriate upstream and downstream interfaces that state has been created, and check the S-G packet counters on each router. There are situations where routers will have pin sparse mode state, but the layer 2 infrastructure between them isn't working properly and the packets are getting dropped on the floor. So check both the state and the counters at each hop, and you'll eventually find where the packets aren't being forwarded. Going into the sort of the larger case, if the source is external to your PIN domain, that is, a PIN domain is a set of routers that share a rendezvous point, meaning that the rendezvous points have to talk to each other with MSTP. If the source is external to your PIN domain, first of all, the first thing you do is you go to your rendezvous point and you verify that you have an MSTP source active for that source. If you don't, that's your problem. You got to get one. You have to verify that the multi-protocol BGP next hop in your reachability information is both a pin sparse mode neighbor and that the MSTP here is good. It simplifies things, but that the next hop is on the path towards your MSTP peer. Read the MSTP draft. It's a lot simpler if your peerings are MSTP speakers. Also, verify that you're actually choosing the NLR equals multicast route or reachability as your preferred RPF path. There are ways to screw this up in configuration. BGP distance if you're in a Cisco, picking the wrong rib if you're in a Juniper. Be sure, verify this. Okay, outgoing. Let's say you're transmitting and somebody wants to hear you. What if nobody can hear you scream? Verify that the S-G shows up at your rendezvous point. That's the first place to look. Verify that if it's not, you've got problems, go back to the designated router, make sure it sees the traffic and so forth, and is properly encapsulating to the rendezvous point, et cetera, et cetera. Verify that your rendezvous point is MSTP announcing the source and that it shows up in your peer's MSTP SA cache. When somebody calls your NOC and says, yo, I'm not getting this source, your question to them is, are you seeing the MSTP source active from me? That should be your first question in return. Verify that you've got a pin sparse mode adjacency with your peer and that the modes match. Again, what does the adjacency look like is a question to ask their looking glass or their NOC person. If everything looks good and they should be getting your traffic, verify that you have a peer's interface in the outgoing list for the S-G. If not, that means the join hasn't gotten to you or you haven't accepted that join for some reason. And finally, verify that the packet counters show the traffic going out. Again, look at the counters. Don't just look at the S-G state, also look at the counters to make sure that the packets are really moving. Okay, I've been talking about, where's the drink? I've been talking about the need for active senders and active receivers. When I first got involved with the access grid, the kind of questions I got from my network users were, I can't hear somebody over there. I can't see their video. And then they would go to lunch and expect me to fix it while they were at lunch. I can't do that because they turn everything off. What we needed was the ability to have a static source and a static receiver that we could query and know what the reachability, the actual packet reachability looked like. Reachability, I'm using in the wrong sense here. So the good folks at DAST created this for us. We collaborated with them and they generated this for us. You can get this. It's written in Java at that URL. I highly recommend it. It's in Java, so it runs anywhere. What you end up doing is this goes to a web page. Or rather, the server there puts out HTTP and HTML. What you end up with is a matrix. Each beacon does three things. It transmits continuously on a multicast group. It puts packets on the wire, 10 packets a second. The other thing it does is it receives packets from that group. It's an active receiver. The third thing it does is it sends information about who it's receiving back via unicast to a central repository that you can query with a web browser. This lets you tell somebody, for example, when I first got involved in debugging access grid, I called the networking people at a site and I said, your people aren't seeing the traffic from the outside. And they said, well, they're just not sending. We've got multicast set up and it's working great. And it was kind of hard to argue with them because how can I give them real data to tell them there's nothing there? Well, what I can do here is if you look at number 3 here, in that situation I would go to them, and it wasn't, by the way, it wasn't ARSC that I had this discussion with. But in the case of ARSC, what you can see is a horizontal line that's gray. What that means is that they aren't hearing incoming traffic from anybody but themselves. They're not hearing traffic from the 0, from number 1, from number 2, from number 4, number 5, or number 6. A consistent row like that is pretty good evidence that the problem is with the site that can't hear anybody. And you can use this, you can point to another NOC or to another application people and say, look, you're not receiving anything, you've got a problem to work on, okay? Again, ARSC, this was before they got their multicast working. They're not being heard by anybody either. You can look at the vertical column for number 3, in this case sender 3, which is the same as receiver 3. S3, nobody can hear. R0 can't hear number 3. R1 can't hear number 3. R2 can't hear number 3. They can hear themselves, but numbers 4, 5, and 6 can't hear number 3 either. This is, again, pretty good evidence that that site is isolated. The problem isn't with the outside world. The problem is with that site and their peerings with their upstreams and their peers. This tells you that information. If you've got two sites, where's a good example on this page? There are sometimes situations where, which one is this, number 2? There are situations where you can get out better than you can come in. These are two problems that you need to work separately. Incoming versus outgoing traffic for a given group. If you look at number 2, everybody, with the exception of number 3, of course, everybody can hear number 2 on this vertical plane. That's what that means. But incoming traffic is either congested or not working properly because there are 3 sources that they can't hear at all, and the other 2 have loss in them, 25 and 40 and 19% loss. And so that tells me that if I was going to be helping that site get multicast enabled, I would first look at reception because it looks like they're not hearing some sources there. Anyway, what I've got here, I couldn't put this on my slide. This is today's beacon, or this was Saturday night's beacon page. It's an 80 by 80 matrix. There just aren't enough pixels to put this up on the slide. So I would recommend, afterwards when you come to pick up your buttons, you come take a look at this. You can also go to the beacon page there and get the hyperlink to the actual server that generated this. You can see right away where the reachability is. Even from back there, you can see how much green there is. That's the good news. Green is actually connectivity that exists. Also, you're seeing blocks of green, which means you've got whole groups that can see each other and can be seen without traffic dropping down. We've got some problems with the beacon. For one thing, it only shows the current state. If you print it out, that's about the only way to keep track of how things were. It'd be nice if we could archive the state over time so we could see when problems occurred. We're working on that. We don't know quite how to visualize evolving state. This is a two-dimensional problem. It really requires you to manage a matrix of reachability from all sources to all receivers because of the inherent branching nature of the problem. I don't know how to keep an 80 by 80 in my head, so I need a picture. Inherently, so if you want to see how this evolves over time, it's a three-dimensional problem. And I'm not quite sure how to represent that in some sort of a rational way. I'm sure some other people will have a great idea, and I really hope I hear about it so it can be done. But I don't know what that is yet. We had some problems when we hit 40 beacons. We've pretty much resolved those. We're up around, this picture here shows an 80 by 80 matrix. We continue to grow. This is a good thing. Please feel free to download the software from the NLANR site that I mentioned and start a beacon. Just leave it running, and that way you can tell, and everybody else can get a better feel for what the internet multicast reachability looks like. So let us worry about the scalability of the server is what I'm saying about this bullet. Another thing about the multicast beacon is that it assumes the any-source multicast model. We don't have an implementation of this that lets us debug things in the source-specific model. There's several reasons for this. One reason is that it's written in Java, and we're concerned that the SSM support in Java isn't there yet. I'd very much like somebody to tell me, oh yes it is, but we don't see it yet. Okay, some of the building blocks I've talked about. MBGP, the multi-protocol BGP. This is the older RFC. Use the one in the earlier slide. This is implemented by Juniper and Cisco in their major releases, especially the service provider releases for Cisco, and in the 12.0 and 12. I think it's in the later 12.0, and it is in the 12.1 base release. I know this. The access grid community has used Juniper and Cisco the most, so those are the ones I know the most about. There may be others. MSDP is implemented by Juniper, Cisco, Foundry, and so forth. It meets the multiple interoperating implementations test of an RFC. It's just a matter of time before it gets codified as an RFC codified. PIM sparse mode is implemented by a whole raft of vendors, Cisco, Juniper, Foundry, Extreme, Marconi, Nextop Technologies has it for your Unix boxes, et cetera, et cetera. So in other words, you can put this in your network. You don't have to do a forklift upgrade to Cisco in order to get PIM sparse mode anymore. It used to be you had to, you don't have to anymore. Edge multicast building blocks. IGMP v2 is widely available in layer 2, IGMP snooping switches, and layer 3 devices like routers and hosts. And IGMP v2 is widely available in most host operating systems. It's in boardware from Windows 95 on. It's in all the BSDs, of course. It's in Linux, name your operating system, Solaris, Hyrix, whatever. IGMP v2 is there. It's been there for a long time. It just works. IGMP v3 is coming soon. It's not quite there yet. It's a matter of getting it implemented and in the appropriate places. It's available in layer 3 devices, that is routers now. Cisco and Juniper, the latest release from Juniper, has IGMP v3 support. I think it's in the 12.1T train on Cisco, IGMP v3. It's not there yet in the layer 2 devices. I don't think IGMP v3 snooping works yet, so I can't really deploy it in my wide layer 2 network. IGMP v3 will be available in Windows XP, Whistler, for boardware. I wish it was going to be available as a service pack in some of the earlier Windows. It's not there yet. Currently, it's available as a patch in Linux. And last time I looked, that patch was not compatible with more than one processor, which limits its availability, and I don't think it's in the core Linux kernel yet. IGMP v3 is coming, it's not there yet. Because it's not there yet, there are some ugly hack workarounds. If you don't want to deploy IGMP v3, there are some ways to emulate IGMP v3 using things like the URL redirect, where you make a pseudo HTTP request off for some URL, and the router intercepts this request magically and says, oh, you meant to do IGMP v3. It works. But it works. That's all I can say. North American, we are in North America, of course. Multicast status, I can speak to the research and sort of government networks better because that's where I work. ESNet, Abilene, VBNS Plus, and NRAN are all running these protocols amongst themselves and with their customers and peers. This is a good thing. We've been working with typically the problems we see. Well, we'll get into that. The regional and institutional networks are currently the most common stumbling blocks for multicast applications. When I say regional, I mean things, it used to be that some of the gigapops weren't multicast enabled. That's getting a lot better now. I'm finding that the institutional networks, like within a university or within a national lab or within a company, just are the most difficult stumbling blocks. A lot of reasons for that. One of the best reasons for that is that they've worked very hard to find an integrated piece of routing code that'll do all of their protocols, AppleTalk, DECnet, IPX, make your list. And they really don't want to have to go through the test process to add another version of code that may break something else in their network. That's a good reason. A less good reason is because they have routing boxes that can't be upgraded, either because they don't have enough memory or they've been engineered or their vendor doesn't do pin sparse mode right. We've seen those. And of course we've seen them that I'm just overworked, I don't have time, we work around that as well. There exist some meeting points. My colleague Linda Winkler, she works right around the hall from me. She's one of the engineers on StarTap in Chicago. Come to StarTap if you're an international, and multicast is available there, just like all the other services from StarTap are. The international and commercial networks are coming online. You'll see some, on this reachability, you'll see some other networks. Vario is running, we've got a peering with Vario. I think I mentioned them earlier with this other router. And I think SprintLink, if I'm not mistaken. Anyway, there's Marshall Eubanks of Multicast Technologies handles the commercial side of the world a lot better than I do. I can tell you about the research networks better than the commercial side. Good news is we're seeing more and more penetration of multicast into the provider networks. That's what I had to say. I'd be very interested in hearing your questions, comments. Feel free to come up and grab some pins. They're on both ends here. Now that you understand what these pins are saying, I'd be very grateful if you could wear them around and tell other people what they mean when they ask what this sort of opaque saying is. Also, feel free to come up and take a look at this reachability graph. And I'm glad to take questions.
Jerry Anderson, Level 3. If you were a customer going to a service provider and you wanted to buy multicast, what questions would you ask and why?
As a matter of fact, I've been asked that question. And the first question I would ask is, how are you providing it? Or are you providing multicast? There's a company that's taking the access grid technology, is trying to commercialize it, and they're finding that one of the biggest barriers to commercialization of the access grid technology is the lack of multicast from commercial providers. I would just make sure that they're running the current multicast protocols. If you're doing standard BGP peering with your customer, make sure that your upstream provider you're evaluating also does pin sparse and NBGP. If your customer wants DVMRP, think that question equivalent to your customer wants RIP from you. Okay, it's just it just doesn't match what the real world is these days. Does that help? Okay. Anybody else? Well, we're about 12 minutes early, so I thank you all for coming.